Good morning to everyone. Today we are going to see a problem on gas turbine cycle with regeneration. Right. So here is a problem. We are having a gas turbine plant with inlet temperature of 15 degrees Celsius and compressing with 4 times that of initial pressure, and compressor's efficiency is 85%. So after compression, the air is passed into a heat exchanger, which is the regenerator, heated by turbine exhaust, before reaching combustion chamber. So after the combustion, the combusted gases is let into a turbine. The turbine inlet temperature is 600 degrees Celsius and efficiency of turbine is 80%. So neglecting the losses, treat the working fluid to be air. You have to calculate thermal efficiency and work ratio of the cycle. If heat exchanger is a perfect heat exchanger, that is, it is giving out entire heat from the exhaust to the regenerator, and heat exchanger gives 85% of heat to the regenerator. So for the two cases we have to find thermal efficiency. With these two cases we can infer the importance of regeneration, right? So we have to take R and gamma as constant values of air. Now we will move on to the problem. So this is the schematic diagram. So air is compressed, and then the compressed air is heated by regenerator, which is getting heat from the exhaust of the turbine, and then it is passed into air is passed into the combustion chamber where fuel is supplied and combustion takes place, and combusted gases runs the turbine and work is generated. After the generation of work, the exhaust from the turbine is used to heat the air from the compressor. This is the simple gas turbine cycle with regeneration, right? Now if you see the given data, so temperature 1 is 15 degrees Celsius, that is 288 Kelvin. So inlet of the turbine, that is 15 degrees Celsius and it is 288 Kelvin, and pressure ratio is 4. In the question it is given as, what is given in the question? The question it is given as 4 times the initial pressure. So we are taking pressure ratio as 4 and gamma is 1.4. Compressor efficiency is 85% and turbine efficiency is 80%, right? So temperature at the inlet of the turbine is 600 degrees Celsius. We are taking it as 873 Kelvin and R is given 0.287. For the case 1, perfect regeneration. Case 2, 85% regeneration, right? So we will see what perfect regeneration and 85% regeneration when we are getting into that section, right? So first step, we have to find the Cp value. We are given R and gamma. So Cp equal to gamma R by R gamma minus 1, which is coming as 1.005 kilojoules per kilogram Kelvin. And then you have to find temperature after isentropic compression, right? Temperature after isentropic compression. So temperature after isentropic compression is T2s will be equal to T1 Rp power gamma minus 1 by gamma, which is equal to 428 Kelvin. So isentropic efficiency is T2s minus T1 by T2 minus T1, as we saw in the previous problem. So actual temperature after compression is 452.7 Kelvin. So higher temperature than the isentropic one, right? So higher temperature means we are giving more work than the isentropic work. Isentropic work is minimum possible work. Actual work should be greater than the isentropic work, right? So actual work will be equal to Cp into T2 minus T1, which accounts to 165.52 kilojoules per kilogram. Now we have to find temperature after isentropic expansion. So temperature after isentropic expansion, T4s will be equal to T3 by Rp power gamma minus 1 by gamma, which will be equal to 587.448 Kelvin. So that is the temperature after isentropic expansion, right? So now turbine work will be equal to T3 minus T4, that is actual work derived from the turbine, and T3 minus T4s is maximum possible work from the turbine. So actual work divided by maximum possible work is turbine work, but whereas minimum possible work by actual work is compressor efficiency. Turbine efficiency is actual work by maximum possible work. So in the ideal case, turbine should extract maximum work. Similarly, in ideal case, compressor we are supplying work should be as minimum as possible for an ideal case, right? So using these two formulas, we are calculating T4 and T2 respectively. So T4 is coming as 644.58 Kelvin, 644.58 Kelvin. Turbine work will be equal to Cp into T3 minus T4, which is equal to 229.56 kilojoules per kilogram. Net work is calculated as WT actual minus W compressor actual. Net work is nothing but summation of all the works available in the system. So summation of all the works here means turbine work, which is positive, and compressor work is negative because we are supplying work to compressor. So therefore compressor work is negative. Turbine work, we are extracting work from the turbine, therefore turbine work is positive. So 229.56 minus 165.52, which is coming as 64.04 kilojoules per kilogram. Now we have two work ratios. One is back work ratio, which is the ratio of compressor work and turbine work, which is coming as 0.72 or 72%, and work ratio is ratio of net work and turbine work, which is coming as 27.89%. Now we are coming to the two cases of regeneration, that is perfect regeneration and 85% regeneration. Now we will see what regeneration is. So regeneration means heating the air from the compressor with the combusted gases from the exhaust, right? So if entire heat available for regeneration, that is T4 minus T2 into Cp into T4 minus T2. So T4 is here, exhaust of the turbine, and T2 is inlet of the regeneration. So Cp into T4 minus T2 is the actual heat available for regeneration, right? So if that entire heat is utilized, then Cp into T5 minus T2 should be equal to Cp into T4 minus T2. In other words, T5 should be equal to T4 if regeneration is perfect, right? So we are taking T4 equal to T5, assuming that effectiveness is 1. So we are calculating heat to input Cp into T3 minus T5, which is coming as 229.56 kilojoules per kilogram. Therefore thermal efficiency equal to W net by heat input, which is coming as 27.89 Kelvin. So now effectiveness is 85%. That is 85% of heat available is used for regeneration. That is T5 minus T2 is equal to 85% of T4 minus T2. So 85% of heat available is utilized, that is effectiveness equal to 0.85. So 0.85 will be equal to Cp into T5 minus T2 by Cp into T4 minus T2. Cp and Cp will get cancelled. So 0.85 equal to T5 minus 452.7 by 644.58 minus 452.7. T5 is coming as 615.8 Kelvin. So heat input should be equal, then it will be equal to 258.49 kilojoules per kilogram, and thermal efficiency is calculated as 24.77%. Now if we carefully observe these two cases side by side, so here on the left hand side you are having effectiveness as 1. We require 229.56 kilojoules per kilogram of heat to be supplied, right? If effectiveness of heat exchanger is 1, if effectiveness of heat exchanger is 0.85, we require 258.49 kilojoules per kilogram. If regeneration is perfect, we are require only 229.56 kilojoules per kilogram of heat. If regeneration is 85%, we require a greater amount of heat. If it is 0.8, we will require even more amount of heat. So if effectiveness decrease, the heat input will increase. Similarly, the efficiency is calculated as 27.89 for perfect heat exchanger. So here for 85% effective heat exchanger, the efficiency is coming as 24.77%. So if effectiveness of heat exchanger drops, thermal efficiency will drop. Therefore, the regeneration is done to minimize the fuel. So minimize the fuel supplied or minimize the energy supplied to the plant, right? If you are using turbine exhaust to heat the air, in combustion we require only lesser amount of heat, right? So that is the concept of regeneration. So regeneration is to minimize the fuel or minimize the energy supplied in combustion, right, to achieve the same or equivalent amount of work. How we are minimizing the energy is supplied. That is the concept of regeneration, right? So we will solve the same problem with effectiveness 0.8 and effectiveness 0.75. Then we will observe the decline in efficiency and increase in heat supplied. So now we will infer the concept of regeneration is to reduce the fuel supplied to the gas turbine power plant, right? So with this we will close this video. We will see gas turbine power plant with reheat